What if the universe sent us a message, written not in words, but in dust and ice? What if that message came from far beyond our solar system, carrying stories from another star? You see, when the interstellar object 3I Atlas swung past the sun, something about it didn't add up. Astronomers expected a quiet traveler, shedding a bit of gas as sunlight warmed its frozen skin. But instead, telescopes caught sight of powerful jets stretching millions of kilometers, bursts of material that seemed too energetic, too persistent, too, well, unnatural. And Avi Loeb, the Harvard astrophysicist known for his daring questions, looked at the numbers and asked, did 3I Atlas break apart at Perihelion, or is it something else entirely? Think of it, a fragment from another star, gliding through the inner solar system, acting in ways no comet should. Its jets told one story, its brightness another, and its size yet another. If it truly lost 16% of its mass in a single swing around the sun, then the surface area needed to absorb that much solar energy should have been enormous, far larger than what we observed. So what are we missing? Could this be a natural body that fractured under stress, or a visitor that doesn't follow nature's usual rules? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world, and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So, let's continue. When we look at the night sky, we imagine it as calm, eternal, unchanging. Stars glimmer in their ancient silence, and the planets follow their endless dance around the sun. But every now and then, something unusual crosses that familiar stage, something that makes even seasoned astronomers pause and whisper, wait, what is that? 3I Atlas was one of those somethings, a visitor not from our solar system, but from the cold interstellar dark between the stars. When it passed its closest point to the sun, its perihelion, it left behind a trail of questions as bright and mysterious as its faint blue tail. You see, after perihelion, the images began to arrive. Observatories caught sight of jets, massive, luminous plumes of gas and dust, stretching millions of kilometers into space. One jet pointed roughly 1 million kilometers toward the sun, the other about 3 million kilometers away, as though the object itself were caught in a tug-of-war between two unseen forces. For an ordinary comet, that kind of activity would unfold slowly, quietly, over the course of months. Yet here, it seemed to have happened almost overnight. Avi Loeb looked closely at those numbers. The jets were too strong, the mass loss too rapid. If the material were escaping at the expected rate of about 0.4 kilometers per second, then for the plumes to extend that far, the process would have to last at least 1 to 3 months. But the brightness variation suggested only days of activity. The math didn't fit. The data didn't hum in tune with the physics we thought we knew. That's where curiosity begins, right there, in the dissonance. So Loeb did what any scientist with a restless mind would do. He began to calculate. From the estimated density of the ejected material and its velocity, he computed a mass loss rate of roughly 5 billion tons each month. That's not a typo. 5 billion tons, streaming into the void like vapor from a cosmic kettle. In total, 3I Atlas might have shed nearly 16% of its mass. If that were true, it would mean its surface was undergoing extraordinary stress. And if such a violent loss were powered solely by sunlight, then the object would need a much larger area to absorb that energy, far larger than the tiny body the Hubble Space Telescope measured at about 5.6 kilometers across. Now, let's pause there. The physics of sublimation, the process where ice turns directly into gas, is well understood. A comet's surface, made of frozen water, carbon dioxide, and other volatile compounds, releases gas when warmed by the sun. But the rate of that release depends on both the composition and the exposed surface area. If 3I Atlas were releasing carbon dioxide, then to account for its observed activity, its surface would need to span a sphere roughly 23 kilometers wide. If the gas were water vapor, that required diameter would grow to more than 50 kilometers. That's 10 times larger than what was actually observed. So what does that mean? Either our measurements were wrong, or something dramatic happened. Perhaps the object fractured, exposing many new surfaces that together absorbed far more sunlight than before. Or, as Loeb cautiously proposed, maybe it wasn't a natural comet at all. Now, that sounds like the kind of statement that makes headlines, but Loeb didn't leap to conclusions. He simply pointed to the mismatch. Science, after all, isn't about believing. It's about noticing. And what he noticed was that 3I Atlas didn't behave like a comet. Its brightness curve, its energy output, the geometry of its tail, all suggested something unusual. The sun had given it more energy than it could reasonably handle, and yet the response didn't follow the usual script. Imagine it for a moment. This small, dark traveler, forged in another solar system long before life even began on Earth, drifts through the interstellar dark for millions of years. No heat, no motion, just silence. Then, by pure chance, it falls into our neighborhood and rushes toward our sun. At its closest approach, the radiation becomes fierce. Its surface begins to vaporize. Jets burst outward, and for a brief moment it shines like a cosmic ember. And yet, beneath that beauty lies a puzzle. The numbers don't work. The comet should have melted more, slowly. The mass loss should have been smaller. Perhaps, as Loeb speculated, it broke apart at perihelion. That would explain the apparent increase in surface area and the intense jets. A breakup could expose fresh ice that had been hidden beneath a dusty crust, allowing sunlight to vaporize it all at once. The resulting pressure could push debris outward at tremendous speed, creating those long tails we observed. But then again, if it did fracture, why didn't we see clear fragments right away? Even the Hubble data showed no distinct pieces at first, only diffuse plumes. Could the fragments have been too faint, too small to detect, or was something else at play entirely? You see, when astronomers talk about comets, they talk in probabilities and approximations. Nature rarely gives us clean answers. We build models, we simulate, we adjust parameters. Yet sometimes an object like 3I Atlas appears, and our models simply fail. It's as if the universe is reminding us that our understanding is still young, that there are pages missing from the book of cosmic physics. Loeb's calculations pointed to a deeper question. If 3I Atlas behaved inconsistently with natural sublimation, what alternative forces might have driven its motion? Could sunlight alone account for the observed acceleration? Could the pressure from escaping gases have been amplified by an irregular shape, perhaps by hollow cavities focusing the outflow like nozzles? Or could something even stranger be responsible, some mechanism we have yet to grasp? And there's another layer here. The jets of 3I Atlas were not evenly distributed. They seem to originate from specific regions, concentrated and directional. That asymmetry complicates the story. A uniformly sublimating body would produce a smoother tail, a more predictable curve. Instead, the observed pattern hinted at complex internal structure, perhaps layers of volatile materials stacked within, each responding differently to the sun's heat. Well, that's the beauty of astronomy, isn't it? Every observation opens a door to more questions. When we look at distant galaxies, or at an interstellar traveler like this one, we're not just gathering data. We're peering into the mechanisms of creation itself. These small, icy bodies carry the fingerprints of the systems they were born in, their chemistry, their structure, their response to heat. All whisper stories about stars that once burned elsewhere in the galaxy. And yet, amid the data tables and spectral graphs, there's something deeply human about this investigation. We're chasing patterns, looking for order in the chaos, trying to reconcile what we see with what we know. Loeb's insistence that something doesn't add up isn't a claim of certainty, it's a statement of wonder. It's the same impulse that has driven science since its beginning, to stand before the unknown and admit, quietly, I don't yet understand. In a sense, Three-Eye Atlas became a mirror. Through it, we could see both the vastness of the cosmos and the limits of our own reasoning. Our instruments captured streams of dust and gas, but what they truly recorded was the moment when a mystery entered our neighborhood and refused to explain itself. And perhaps that's what makes it so compelling. Whether it shattered at perihelion or merely flared in some unexpected way, Three-Eye Atlas forced us to look again at how fragile our assumptions are. In that bright blur, just beyond the sun's glare, lies a reminder that even now, in the age of space telescopes and simulations, the universe still surprises us. So we stand at the edge of knowledge, watching a faint smudge of light drift away into the dark, carrying our questions with it. What was it made of? How did it survive such an encounter? Did it fracture, or did it reveal a process we've never seen before? These are not just technical puzzles. They are invitations to look deeper, to listen more carefully to what the cosmos is trying to tell us. Because you see, every observation like this one stretches our imagination a little further. It reminds us that science is not a collection of answers, but a journey of questions. And as Three-Eye Atlas continues on its silent path, leaving behind only traces of its strange behavior, we find ourselves preparing for the next step, the moment when we must place this event within the larger story of interstellar visitors and ask what it means for our understanding of the space between the stars. When we talk about Three-Eye Atlas, we are not just talking about another comet. We are speaking about something that does not belong here, an interstellar object, a wanderer from another star system, and that in itself is extraordinary. You see, our solar system has its own rhythm, its own family of planets, asteroids, and comets, all bound by the gravity of our sun. But every so often, a stranger crosses the boundary. It moves too fast to be captured, too free to belong, carrying with it the signature of another world. That's what makes Three-Eye Atlas so fascinating. It's not simply a ball of ice and dust, it's a messenger from a distant system, perhaps born around a star that no longer even exists. Before Three-Eye Atlas, there were only two confirmed interstellar visitors: One-Eye Oumuamua and Two-Eye Borisov. Each of them brought its own set of mysteries, and each changed how we think about our place in the galaxy. Oumuamua, discovered in 2017, had no visible tail, yet it accelerated as though pushed by some invisible hand. Borisov, found 2 years later, looked more like a traditional comet, though its composition hinted at an origin beyond anything we had seen before. And now, Three-Eye Atlas has entered this strange lineage, our third clue in a growing cosmic puzzle. Interstellar objects like these are rare, so rare that for decades astronomers doubted we'd ever find one. Space is vast, and the regions between stars are unimaginably empty. For a piece of matter to drift across that darkness and just happen to pass through our narrow window of observation, it's almost miraculous. Think of it. In the endless ocean of space, these objects are like driftwood, carried across interstellar tides, remnants of worlds torn apart by gravity or collisions long ago. They wander for millions, maybe billions of years, until by pure chance they enter the light of another star, and we, for a fleeting moment, get to see them. And what do they tell us? They tell us that our solar system is not alone in producing such fragments. Each star system, with its own planets and debris, must send out countless objects over cosmic time. Every time a planet forms, collisions occur. Every time a star ages, its gravity shifts, scattering loose material into space. Some of that material escapes entirely, becoming interstellar. So, in a way, the galaxy is full of these travelers, though most will never be found, never be seen. Only a few pass close enough, bright enough, to be caught by our telescopes. 3i Atlas, then, is more than an object. It is evidence that we are part of a greater galactic ecosystem. It is a tangible link between star systems, proof that the dust of one world can drift into the neighborhood of another, and that has profound implications. Because if solid material can cross the void, then so can the ingredients of life. The seeds of chemistry, the carbon, oxygen, and nitrogen that make us, may be shared across the stars. When we observe a comet from another system, we are, in some sense, looking at a fragment of our galactic history. Now, the discovery of 3i Atlas came at a time when our instruments were ready for it. Wide-field surveys like Atlas scan the sky every night, mapping transient phenomena. When the data first showed this faint, fast-moving point of light, astronomers noticed its unusual trajectory, an orbit that wasn't closed around the sun. It was hyperbolic, meaning it would come in, swing around, and never return. That single fact told us everything. This was an interstellar traveler. It had come from the far beyond, carrying the physical memory of another system's birth. The idea of an interstellar object seems almost poetic, doesn't it? A piece of matter adrift between stars, unclaimed, unsheltered, and yet persisting. But scientifically, it's also crucial. These objects test our understanding of formation processes. They allow us to compare how other systems behave. What materials solidify in their outer reaches? How are their ices layered? What ratios of carbon and oxygen do they hold? Every observation becomes a data point in the story of galactic evolution. In the case of 3i Atlas, what struck astronomers was how active it became near the sun. That behavior alone sets it apart. Borisov, too, had shown strong outgassing, but the sheer scale of Atlas's activity, those immense jets we spoke of earlier, suggested a volatility beyond what we expected. That raises questions about its origin. Could it have come from a younger, more energetic system where volatile compounds are abundant? Or perhaps from a binary star region, where gravitational interactions might have stripped away material in ways unlike anything in our own system? When you think about it, these interstellar visitors are time capsules. They preserve within them the chemical fingerprints of their home environments. By analyzing their spectra, we can detect specific molecules, carbon monoxide, water vapor, cyanides, that reveal not just what they're made of, but how they formed. For example, high levels of carbon dioxide relative to water can suggest formation in colder, more distant regions from a parent star. A dominance of hydrocarbons might hint at a protoplanetary disk rich in organic precursors. In that sense, each interstellar object is like a frozen fossil, a relic of a time and place we can never visit directly. There's also the question of probability. How often should such visitors appear? Before Oumuamua, most models predicted maybe one every few centuries. Then we found 3 in less than a decade. That suggests either we've been lucky, or that the galaxy is far busier than we thought. Perhaps the vast spaces between stars aren't as empty as we once imagined. Perhaps countless fragments are passing through right now, unnoticed. too faint for our instruments to detect. It's humbling to think that we might be surrounded by travelers from other worlds and simply lack the eyes to see them. When Loeb and his colleagues talk about interstellar objects, they often touch on something philosophical. These objects challenge not only our physics, but our sense of belonging. For so long, we imagined our solar system as a closed garden, isolated by the gulf of interstellar space. Yet every visitor like 3i Atlas reminds us that the boundaries are more porous than we believed. The universe is not a collection of isolated islands. It's an ocean, with currents of matter flowing between stars. And of course, there's the inevitable human question. Could any of these objects carry traces of life or of technology? Loeb, known for his willingness to consider bold possibilities, has often said that science must remain open to all explanations, however uncomfortable they may seem. He doesn't claim 3i Atlas is artificial, but he insists we must not dismiss the idea prematurely, because after all, every great discovery begins as an anomaly. Still, even if 3i Atlas is entirely natural, its existence expands our sense of wonder. It means that the dust beneath our feet and the ice within these travelers share a common ancestry. Somewhere, long ago, clouds of gas and dust collapsed to form stars. Some of those stars gathered planets. Some of those planets broke apart, scattering debris into interstellar space. And now, across the eons, those fragments come drifting back to tell their silent stories. When we detect such an object, we are not merely looking outward, we are looking backward into cosmic history. Each interstellar visitor is like a memory, a relic of the processes that built the Milky Way itself. They reveal how material circulates between systems, recycled and reborn in endless cycles of creation and destruction. And if the same physics applies everywhere, then our story, the story of Earth, of life, may be written into those cycles too. It's remarkable to think that the same elements composing 3i Atlas, carbon, oxygen, nitrogen, were forged in the hearts of stars long gone. And through the quiet, unending drift of interstellar matter, those elements travel, finding new homes, forming new worlds, perhaps even new minds to wonder at their origin. In that sense, 3i Atlas isn't just a comet. It's part of a cosmic conversation that began long before us and will continue long after. As we follow its trajectory, we find ourselves drawn into that conversation. We ask, what forces shaped this object? What temperatures, what pressures, what collisions carved its path? Each observation we make is a fragment of an answer. But the real message, perhaps, is this. The universe is alive with motion. Stars form, die, and scatter their remains, and from those remains come travelers like 3i Atlas, reminders that creation and destruction are inseparable. And so, as the comet fades into the blackness, leaving only data points and equations behind, we begin to look wider. We begin to place it within a larger framework, the family of comets, asteroids, and icy bodies that dance around our own sun. Because to understand how strange 3i Atlas truly is, we must first understand what is ordinary. What does a typical comet do when it nears the sun? How does ice behave in the vacuum of space? And why, in this case, did the expected rules seem to fail? Well, that's where we're heading next. The story of sublimation, of energy and ice, of how sunlight breathes life into frozen rock, awaits us just beyond this point. And as we turn our gaze from the interstellar dark back toward the warmth of our own star, we begin to see how the mystery of 3i Atlas connects to something universal. The ancient dance between light and matter, between fire and ice. When sunlight touches a comet, it awakens something ancient. The ice begins to whisper, to move, to breathe. What was frozen for millions of years suddenly becomes alive again, releasing gases that have been trapped since before the birth of our world. This process, the transformation of solid ice directly into gas, is called sublimation. It's one of those quiet miracles of physics, a dance between energy and matter that unfolds in the most hostile vacuum imaginable. And for understanding 3I Atlas, it is absolutely central. You see, sublimation is what gives a comet its tail. It is what turns a cold, inert rock into a glowing traveler across the inner solar system. When a comet approaches the sun, its surface begins to warm. The outer layers, made of frozen water, carbon dioxide, methane, and other volatiles, absorb that energy. But because space is nearly airless, these ices cannot melt. They skip the liquid stage altogether, turning straight from solid to vapor. That gas expands outward, carrying dust with it, forming jets and halos that we see as the coma and tail. It sounds simple enough, but the physics behind it is delicate. Sublimation depends not just on temperature, but also on pressure, composition, and the depth of each ice layer. Every comet is a unique blend of ingredients, frozen at different distances from its parent star. Some contain more carbon dioxide, which sublimates easily at low temperatures. Others are rich in water ice, which requires more heat. The result is that each comet responds differently to sunlight, like musical instruments tuned to different keys. For a typical comet in our solar system, the process is gradual. As it moves inward, the rate of gas loss increases smoothly, following predictable curves of temperature and distance. By the time it reaches the inner solar system, it shines brightly, but behaves as expected. The energy from the sun drives a steady rhythm of outgassing, a balance between heat absorbed and mass lost. Yet with 3I Atlas, that rhythm seemed broken. Its outgassing did not follow the usual cadence. It surged, abruptly, almost violently. To understand why that matters, we need to picture what sublimation looks like up close. Imagine standing, hypothetically, on the surface of such an object. Beneath your feet lies a crust of dusty material, fragile, porous, riddled with microscopic cavities. The sunlight hits it, and within seconds, tiny jets begin to erupt as buried ice pockets flash into vapor. Each one releases a plume that carries grains of dust, creating miniature geysers that can shape the comet's entire trajectory. Over time, the surface changes, crumbling and darkening as the most volatile compounds are depleted. But for an interstellar object like 3I Atlas, the surface we see might be unlike anything found in our solar system. It has traveled through interstellar space for millions of years, bombarded by cosmic rays, stripped of lighter molecules, and perhaps coated with a layer of organic tar. Beneath that hardened exterior could lie pristine ice untouched since the formation of its original system. So when it came near our sun, that outer crust may have cracked suddenly, exposing new material that had never before seen starlight. The result, an explosive surge of sublimation. Now, let's consider the energy itself. The sun emits roughly 1,300 watts per square meter at Earth's distance. A comet closer to the sun absorbs even more. But not all of that energy goes into heating. Much of it is reflected or radiated away. Only a fraction penetrates deep enough to trigger sublimation. This balance determines how quickly the ice turns to gas and how much pressure builds beneath the surface. In some cases, if the gas cannot escape quickly enough, it can fracture the body from within. That's one of the reasons many comets split as they near the sun. Their own escaping gases tear them apart. So when we talk about sublimation, we are really talking about a battle between sunlight and structure. Light delivers energy. Matter resists until it can no longer hold. The energy stored in a photon may seem tiny, but multiplied across millions of square meters and thousands of years, it shapes the destinies of worlds. 3i Atlas appeared to behave as if it were losing mass faster than that balance would allow. For the jets observed to stretch millions of kilometers, the gas must have been escaping at tremendous rates, and that, in turn, means that something unusual was happening beneath the surface. Perhaps the crust had collapsed, exposing interior layers, or perhaps the composition itself was unlike any we've seen before. Maybe it contained supervolatile compounds that reacted violently to the sun's heat. Or perhaps it harbored a porous network that allowed gases to build up and burst outward in powerful eruptions. In the silence of space, these events are invisible to the eye. But our instruments catch their echoes. The light reflected by the dust, the shape of the coma, the spectrum of the gases. From those clues, scientists reconstruct what might be happening inside. And in the case of 3i Atlas, those clues refuse to fit into any neat category. The rates were too high, the energies too great. Loeb's calculations, as we discussed earlier, showed that if this outgassing were due solely to sublimation, the required surface area would be vastly larger than observed. That left us with two choices. Either the comet had fractured, dramatically increasing its exposed area, or the process at work was not standard sublimation at all. But let's linger a moment longer on the beauty of the process itself. Sublimation is not just a mechanism, it's a kind of cosmic breath. Each molecule that escapes a comet carries with it a trace of light, a bit of warmth, a signature of its home system. When those molecules scatter sunlight, they create the soft glow that we see even from millions of kilometers away. That glow is more than reflection. It's memory made visible. It tells us where the object came from, what it's made of, how long it has wandered. You could say that sublimation is the language of comets. Through it, they speak to us across the vacuum, revealing their secrets not in words, but in the way they shine and shed. And for scientists like Loeb, decoding that language is an act of both calculation and imagination. The numbers must align with physics, but behind the equations lies something poetic, a recognition that these frozen relics are not dead at all. They are living, changing, dynamic entities, shaped by light itself. When 3i Atlas began to outgas so dramatically, telescopes captured faint shifts in its brightness and structure. The jets seemed to pulse, as though responding to cycles of sunlight and rotation. That rhythm might tell us something about its shape. Perhaps it was spinning unevenly, exposing different faces to the sun in turn. Each burst of light, each flare, could mark a moment when a new layer of ice was exposed. By studying those pulses, astronomers can infer not only rotation rates, but internal structure, density, and even possible points of weakness. And yet, despite all our instruments, there remains so much we cannot see. Sublimation occurs on scales too fine to resolve, governed by microtextures of dust and ice smaller than a grain of sand. The way gases percolate through those pores, how they build pressure, how they burst. These are mysteries still being explored in laboratories on Earth. Scientists recreate cometary surfaces in vacuum chambers, exposing them to light to watch how the gases escape. Each experiment brings us a little closer to understanding what a comet feels when it meets the sun. But 3i Atlas, being interstellar, might defy even those models. Its ices could contain exotic isotopes, formed under different cosmic conditions. The ratio of deuterium to hydrogen, for example, might reveal whether it formed closer to or farther from its original star. Its carbon compounds could show signs of radiation processing over eons. Each of these details is a clue, and together they could tell us whether interstellar comets follow the same physical rules, or if they are products of environments we can only imagine. And that brings us to a deeper thought. Sublimation, at its heart, is transformation. It's the moment when matter changes state, when solid becomes gas, when stillness becomes motion. In that transformation lies a metaphor for the universe itself. Everything that exists is in motion toward change. Stars burn, planets form, life evolves, and even ice in the deep dark of space eventually yields to light. To study sublimation, then, is to study impermanence, the constant negotiation between energy and structure that defines all things. Perhaps that is why comets hold such fascination for us. They remind us that nothing stays frozen forever. Even the coldest, most distant body will one day feel the touch of light, and in that touch, it will begin to let go, to release, to transform, to shine. So when we watch a comet like 3I Atlas shedding its ancient ices into space, we are witnessing the same process that has shaped planets and atmospheres since the beginning. Without sublimation, there would be no comas, no tails, no delivery of water to young worlds. It's possible that comets like this one once carried the seeds of oceans to Earth itself. In that sense, sublimation is not just physics, it is creation. Still, in the case of 3I Atlas, something about that creation seemed too fierce, too fast. The rates of gas loss, the brightness, the scale of its plumes, all suggested that sunlight alone might not be the full story. The equations of energy transfer, which we'll explore next, show that the amount of radiation a comet receives depends critically on its surface area and reflectivity. For a small body to sustain such activity, its ability to absorb and distribute energy must be extraordinary. And so, as we turn to that question, the question of how the sun's energy interacts with matter so far from equilibrium, we step from chemistry into thermodynamics, from the beauty of change into the mathematics of power. Because the next mystery waiting for us is not simply what 3I Atlas was made of, but how it managed to harness so much energy from the light of a single star. Energy. That's really where everything begins. Every comet, every planet, every flicker of life that has ever existed depends on how light and matter share it, store it, or let it go. When we talk about 3I Atlas and its strange outburst, we are really asking a simple question with cosmic consequences. How much energy from the sun did it actually absorb, and what did it do with it? You see, sunlight is both the sculptor and the destroyer in this story. It is the hand that carves the comet's surface, that pulls gas from ice, that drives those astonishing jets we spoke of earlier. Without sunlight, a comet is just a cold rock drifting in silence. With it, the rock becomes alive with movement, shedding light and vapor, and sometimes, if the balance is wrong, tearing itself apart. The energy reaching any object in space depends mainly on two things: its distance from the sun and its surface area. The closer it comes, the stronger the radiation it feels, falling off by the square of the distance. At Earth's orbit, each square meter of surface receives about 1,360 watts of solar power. But at the distance of Mercury, that number is nearly 7 times higher. For a comet like 3I Atlas, which dove close to the sun, the difference between survival and destruction was measured in those multiplying factors of light. Now that energy doesn't all get absorbed. Some of it bounces away, reflected back into space depending on how bright or dark the surface is. We call that the albedo, and it matters deeply. A bright, icy surface reflects sunlight and stays cooler. A dark, carbon-rich crust, on the other hand, drinks in light like ink. The difference between a high and low albedo can determine whether the ice beneath stays dormant or erupts into a storm of sublimation. When we look at 3I Atlas, the evidence suggests it was darker than expected, meaning it absorbed more heat than a typical comet would. That could explain its sudden, almost violent reaction near perihelion. But to make sense of this, let's walk through the physics in our minds. Imagine sunlight as a rain of tiny packets of energy, photons, each one carrying a small but precise amount of momentum. When these photons strike a comet's surface, some are reflected, some are absorbed, and some are scattered. The absorbed ones raise the temperature of the material, shaking the molecules within until they break free. Every atom that escapes carries away a little of that energy as heat. Multiply that process by trillions upon trillions of molecules, and you get the shimmering tail that stretches behind the comet. For a comet 5 or 6 kilometers across, like 3I Atlas, the amount of solar energy absorbed is immense, roughly equivalent to several million megawatts. But energy alone isn't enough. What matters is how efficiently that energy can reach the ices buried beneath the surface. In some comets, a thick layer of dust acts as insulation, slowing the transfer of heat. In others, fractures and cavities allow sunlight to penetrate deeper, reaching reservoirs of volatile compounds that erupt when warmed. This interplay between heat flow and structure determines whether a comet's activity rises gently or explodes in bursts. Loeb's analysis suggested that the energy available from sunlight, given the measured size of 3I Atlas, was not sufficient to explain the rate of mass loss we observed. To produce jets extending millions of kilometers, the comet would need to radiate far more material than that small surface area could ever heat. If it were made of carbon dioxide ice, its effective absorbing surface would need to be about 23 kilometers across. If water ice dominated, the figure would jump to 51. Yet the Hubble data gave a diameter of only 5.6 kilometers. The discrepancy is vast, almost an order of magnitude. That's why surface area plays such a decisive role. In the equations that describe energy absorption, every watt of solar power must be spread over the surface exposed to the sun. Increase that area, and the total energy intake rises proportionally. If 3I Atlas had fragmented at perihelion, creating a cloud of debris that together presented a much larger collective area, the observed energy release would suddenly make sense. The sunlight would have had far more real estate to work with. But if the body remained intact, then something about the process was amplifying the energy effect beyond what geometry alone could explain. Perhaps then the comet was not uniform. Suppose it had regions of extreme porosity, honeycombed with voids that allowed sunlight to reach deeper layers, effectively multiplying the surface area from within. Or imagine fissures that channeled heat and gas outward, creating concentrated jets like nozzles. In that case, the same amount of energy could produce a much greater visible outflow. The physics becomes nonlinear, small changes in structure leading to enormous differences in behavior. There's a kind of poetry to it. The same sunlight that nurtures life on Earth, that warms our seas and powers our winds, can also tear apart a traveler from another star. Energy, in that sense, is neither good nor cruel. It simply is. It flows, it transforms, and everything that encounters it must decide how to endure. 3I Atlas met that challenge head-on, and for a brief time it blazed in defiance of the darkness. When scientists calculate the energy balance of such an object, they rely on models that account for absorption, re-radiation, conduction, and sublimation. The absorbed energy raises the surface temperature until equilibrium is reached, where the energy coming in equals the energy going out. But if sublimation accelerates faster than the heat can be replenished, the surface cools, slowing the process. Conversely, if cracks expose new ice before the gas escapes, the cycle renews violently. The comet becomes a self-regulating, self-destructive machine. each burst of energy reshaping the very surface that governs it. This is why understanding the relationship between energy and surface area is so essential. The sun doesn't just illuminate, it interrogates. It tests the strength and structure of every world it touches. On a planet with an atmosphere, that energy is filtered, softened, turned into weather. But on a bare comet, there is no protection, only direct confrontation between light and matter. In that confrontation, we see physics laid bare. And yet, there's a deeper philosophical echo here. The way a comet handles sunlight isn't so different from how living things handle experience. Too much energy too fast, and structure collapses. Too little, and nothing changes. There's a balance, a resonance, where transformation can occur without destruction. Perhaps 3i Atlas crossed that line, taking in more than it could withstand. Still, what fascinates me most is how precisely we can trace these invisible exchanges. From millions of kilometers away, by measuring brightness and spectra, scientists can infer temperature variations, albedo, and energy flux. They can tell how fast gases escape, how dust scatters light, even how rough the surface must be. It's like reading a story written in radiation. Every fluctuation in brightness, every flicker of light, is a sentence in that story. If we take those numbers and plot them against time, we get what's called a light curve, a record of how the comet's brightness changes as it moves around the sun. From that curve, we can deduce how much energy is being absorbed and how the sublimation responds. In the case of 3i Atlas, that curve rose far more steeply than expected, suggesting a sudden surge of heat absorption or a rapid increase in surface area, or both. Perhaps, as some have proposed, the comet's rotation brought different facets into view, each with distinct reflective properties. A darker side facing the sun could have triggered the sudden energy uptake. Or maybe the object was spinning so rapidly that centrifugal forces opened new fractures. Every possibility leads back to the same question. How does sunlight shape matter in motion? The universe, after all, runs on this principle. Stars form when gravity overcomes energy loss, planets cool when radiation escapes, and comets erupt when heat finally reaches their hidden reservoirs. Energy transfer governs it all, the great invisible tide that connects every object to every other through the language of light. And that's the wonder of studying something like 3i Atlas. By understanding how it absorbed and released energy, we're not just analyzing a single comet, we're exploring the rules that define all worlds. How much light is too much? How much structure can survive? How far can heat penetrate before matter yields to change? These are the same questions that shaped the early Earth, that drive the atmospheres of exoplanets, that sculpt the destiny of stars. When we look at 3i Atlas through that lens, we begin to see it not as an anomaly, but as a messenger of principles that apply everywhere. Its strange behavior may simply be the extreme expression of natural law, the moment when an object pushed to its limits reveals the edges of our understanding. Still, one detail lingers like a shadow at the edge of all these calculations. Even if the energy budget makes sense, the pattern of activity remains odd. Its jets were uneven, asymmetrical, directed in ways that no simple model can reproduce. That irregularity suggests something more than energy balance alone, something rooted in geometry, composition, and comparison. And that, I suppose, is where our attention must turn next. Because to grasp what makes 3i Atlas so peculiar, we have to set it beside what we already know, against the quiet, predictable behavior of ordinary comets born under our own sun. Only then, in that contrast between the familiar and the strange, can we see clearly where this interstellar traveler begins to defy expectation. To understand what made 3I Atlas so strange, we first have to remind ourselves what is normal, what a typical comet does when it meets the sun. The comets we know best are native to our own solar system, fragments from the ancient disk of ice and dust that once swirled around the young sun more than 4 billion years ago. They come from two great reservoirs: the Kuiper Belt, a region of frozen bodies just beyond Neptune, and the Oort cloud, a vast spherical shell extending halfway to the nearest stars. Most of these comets spend almost all their existence in darkness, frozen solid, until some gravitational nudge sends them inward on long, elliptical orbits. When these icy visitors approach the sun, their behavior follows familiar patterns. First comes a gradual warming, then the release of vapor from volatile ices like carbon dioxide and carbon monoxide. As the comet gets closer, water begins to sublimate, creating a halo of gas and dust, the coma, that reflects sunlight and makes the object visible from Earth. Tails appear, shaped by the twin forces of sunlight and the solar wind, one curved and dusty, the other thin and bluish with ionized gas. The physics is elegant, predictable, almost comforting. Comets brighten smoothly as they near the sun, reach a maximum near perihelion, and then fade as they retreat back into the cold. Even their differences, shape, rotation, composition, fit within this framework. Some comets, like 67P Churyumov-Gerasimenko, which was visited by the Rosetta spacecraft, are rough and double-lobed, with cliffs and sinkholes formed by uneven heating. Others, like Halley's Comet, show repeated cycles of activity that we can model with remarkable precision. We understand how their jets form, how their outgassing changes with distance, and even how the direction of those jets can subtly alter their orbits. Now compare that calm rhythm to what we witnessed with 3I Atlas. It arrived from interstellar space, already moving faster than anything bound to our sun, on a hyperbolic path that would take it back into the void forever. Its rotation period, brightness curve, and spectral signature didn't align with any familiar pattern. The gas jets appeared too strong for the amount of light it received, and their geometry, long, uneven, asymmetrical, hinted at something far more chaotic. While ordinary comets seem to breathe, exhaling in steady, periodic bursts, 3I Atlas erupted. It was as though the sun had awoken a creature that didn't know how to survive its own awakening. That difference, subtle at first, became undeniable as the data poured in. Typical comets near perihelion display a predictable energy balance. The heat absorbed from sunlight drives sublimation, which in turn regulates the temperature by carrying heat away with escaping gas. It's a self-limiting process, a feedback loop. But 3I Atlas broke that loop. Its output increased far more rapidly than the energy input could explain. The result was instability, bright surges followed by unexpected dimming, as if entire regions of its surface were collapsing and reforming in real time. You might think of an ordinary comet as a breathing organism, drawing energy in and releasing it evenly. 3. Atlas, by contrast, behaved like one caught in a panic, overreacting to every pulse of sunlight. That's what drew the attention of Avi Loeb and others who study such anomalies. When the laws of physics seem to hold, yet the numbers don't fit, it means something deeper is happening beneath the surface. There's also the matter of scale. Most comets we know are a few kilometers across and relatively dense, their internal structures compacted by billions of years of slow evolution. 3I. Atlas, however, seemed lighter, more fragile. Its density, inferred from its acceleration and light curve, might have been half or even a third that of typical solar system comets. That would make it far more porous, like an interstellar sponge of dust and ice. Such a structure would react to sunlight very differently. It could allow heat to penetrate deeper, igniting pockets of gas far beneath the surface. When those gases finally burst free, the release could be explosive, creating plumes that dwarf anything seen in local comets. This fragility could also explain its rapid loss of mass. A small, loosely bound object can disintegrate with startling speed once the forces of outgassing begin. Each jet, each eruption, changes the balance of momentum, sending stress waves through the body. In the vacuum of space, there is nothing to slow those changes, no atmosphere to buffer them. A single fracture can propagate across kilometers in seconds. It's a dance between gravity and pressure, a dance that 3I Atlas may not have survived. Another curious point lies in its brightness. Ordinary comets have fairly well understood relationships between their size and luminosity. For 3I Atlas, the observed brightness exceeded what its small nucleus should have produced by several magnitudes. Either the dust it released was unusually reflective, or, as Loeb proposed, the true emitting area was vastly larger than the measured body. Both possibilities stretch our expectations. Highly reflective dust would imply composition unlike anything known, a chemistry formed in a star system with different ratios of carbon and oxygen. A larger emitting area, meanwhile, would mean fragmentation, a disintegration so complete that the comet we saw was already a debris field, shimmering like a cloud of cosmic frost. And yet, even if it had fragmented, something about its motion still refused to fit the ordinary pattern. The non-gravitational acceleration, that tiny push produced by escaping gas, didn't align with its shape or tail direction. It was as if the forces acting on 3I Atlas came from deeper within, not merely from sunlight on its surface. Could internal heat, built up over eons of cosmic radiation, have played a role? Or were there exotic volatiles, perhaps frozen nitrogen or ammonia, that reacted differently under the sun's rays? Each explanation leads to more questions, and that is exactly what makes science so thrilling. You see, by comparing the known and the unknown, we begin to map the boundaries of our understanding. The familiar behavior of solar system comets forms a kind of baseline, a melody the universe has played for billions of years. 3I Atlas was a discordant note, one that doesn't fit the key, forcing us to listen more carefully. And sometimes it's in those dissonant notes that we hear the future of discovery. There's also a geometric aspect to all this. Ordinary comets orbit roughly within the same plane as the planets, the ecliptic. 3I Atlas approached from far above, slicing through the solar system at a steep angle, like a thrown stone skimming through a flat pond. That geometry affects everything. How much sunlight it receives, how its tail aligns, even how we perceive its brightness from Earth. Most models assume comets rotate and sublimate under relatively stable illumination, but an object on a hyperbolic path experiences sunlight as a brief, violent pulse. A few days of intense exposure followed by an eternity of darkness. No wonder it reacted so fiercely. Think, too, about the age of these objects. Our local comets are survivors from the early days of the Sun, their surfaces baked and reshaped over countless orbits. Interstellar objects like 3I Atlas, on the other hand, are likely far older. They could have formed around stars that died billions of years ago, ejected into interstellar space when their systems fell apart. Over that time, cosmic rays would alter their chemistry, converting ices into complex organic residues. The material we saw vaporizing from 3I Atlas might have been older than our planet, older even than the Sun. That thought alone is humbling. In comparing the two kinds of comets, the native and the interstellar, we also find echoes of our own cosmic origin. Both are storytellers of formation, bearing witness to the same universal laws but shaped by different histories. The familiar ones tell us how the sun built its planets. The strangers, like Three-Eye Atlas, remind us that the same process happens everywhere. They are evidence that star systems are not isolated islands but part of a vast galactic cycle of matter. Dust and ice born around one star can someday drift into another's light. And that means, perhaps, that the seeds of planets, even of life, may travel across the stars. Yet for all this grandeur, the puzzle remains grounded in something as simple as temperature, surface, and motion. Why did Three-Eye Atlas react so differently to the same sunlight that governs every other comet? Was it composition, structure, or something altogether unexpected? To answer that, scientists turned to data, spectra, brightness, thermal models, and again, the pieces didn't align neatly. The light suggested certain molecules, the gas output suggested others. It was as if the object were rewriting the chemistry of comets before our eyes. And perhaps it was, because if we learn anything from comparing the ordinary and the extraordinary, it's that nature rarely repeats itself perfectly. Each comet, each world, carries its own set of variables, its own balance between heat and matter, pressure and release. Three-Eye Atlas might simply represent a new category, a bridge between what we think of as natural and what we have yet to define. There's something strangely poetic in that idea, a bridge between systems, between stars, between what we know and what we don't. Maybe that's why we're so captivated by it. The comet becomes a metaphor for curiosity itself, drawn toward light, unraveling as it learns, leaving behind a trail of questions. And it's not lost on scientists that every mystery like this brings us closer to understanding our own origins. By contrasting Three-Eye Atlas with ordinary comets, we refine the tools that can detect future interstellar visitors. We learn what patterns to expect and what deviations to treasure. Each anomaly becomes a signpost pointing toward the unknown. Still, there's a deeper layer yet to explore, the rhythm beneath the light. Because when we examine how Three-Eye Atlas lost mass, we find another mystery. The rate didn't rise smoothly, as physics would predict. It spiked exponentially, as though something within the object amplified itself with every passing moment. That strange escalation of loss, that runaway evaporation, might hold the key to understanding what really happened as it neared the sun. And that, I suppose, is where we must now turn our gaze, to the question of acceleration, of exponential change, and of why Three-Eye Atlas seemed to unravel faster than time itself could explain. When scientists plotted the rate at which Three-Eye Atlas was losing mass, the curve didn't rise gently, as one might expect from a comet responding to sunlight. It climbed steeply, so steeply that it resembled the shape of an exponential function. At first the loss was slow, almost modest, but then within days it began to surge uncontrollably. It was as though something inside the object had crossed a hidden threshold, a point of no return where each release of gas triggered the next, and the next, until the process consumed itself. In that runaway escalation lies one of the strangest clues about what may have happened near its perihelion. You see, natural sublimation, the steady transformation of ice to gas under the warmth of the sun, follows predictable physics. The rate depends on temperature, and temperature depends on distance from the sun. As the object moves closer, the sunlight intensifies roughly with the inverse square of that distance, meaning the heat increases gradually. In a normal comet, that produces a smooth, continuous rise in gas output, a curve that is steep but manageable. Yet for Three-Eye Atlas, the slope of that curve didn't simply follow distance. It shot upward far faster, as though something inside the comet were feeding on itself, a feedback loop of energy and erosion. Avi Loeb noticed this first. He called it not adding up, and for good reason. If the mass loss followed an exponential law, then the surface of 3I Atlas wasn't just reacting to the sun, it was amplifying the reaction. The energy it absorbed was somehow multiplied through structural collapse, fragmentation, or the release of trapped volatiles buried deep within. That amplification would explain the immense jets seen stretching millions of kilometers into space and the sudden brightening that followed. It would also explain why the comet seemed to lose 16% of its total mass in such a short period, a loss that no simple model of sublimation could produce. Let's think about what exponential really means in this context. When a process is linear, each step adds a fixed amount. But when it's exponential, each step multiplies by a factor. In the physical world, that usually signals feedback. In a star, for example, exponential reactions drive nuclear fusion. In a wildfire, heat breeds more heat until everything burns. For a comet, exponential mass loss suggests that every plume of escaping gas weakened the structure, exposing fresh ice, which in turn produced more gas. Each moment of activity created the conditions for even greater activity. The comet became its own engine of destruction. Imagine it for a moment. Beneath a fragile crust of dust, volatile compounds are locked in darkness. The sun's warmth seeps down, perhaps through cracks or porous channels, until it reaches those deeper layers. Gas begins to form, building pressure in confined pockets. When that pressure exceeds the strength of the crust, it bursts outward, carving new vents, widening the cracks. Suddenly, more of the interior is exposed and more sunlight penetrates. The next burst is stronger, faster, hotter. In hours, what began as a whisper becomes a roar. That kind of behavior is what scientists call nonlinear dynamics, the point where small causes lead to disproportionate effects. Once the process begins, it cannot be easily stopped. And because it depends on structure and composition, not just on distance from the sun, it can vary dramatically from one comet to another. For 3I Atlas, which likely carried ices and materials shaped in a different stellar environment, those dynamics could have been unlike anything our models anticipated. Now, consider what happens to such an object as it spins. Rotation plays a crucial role in how energy spreads across a comet's surface. A slow spinner warms evenly, giving gases time to escape without destabilizing the body. A fast spinner, on the other hand, experiences cycles of intense heating and cooling, creating stress between the sunlit and shadowed regions. Those thermal stresses can widen fissures, encouraging the kind of runaway sublimation we're describing. If 3I Atlas were rotating unevenly or tumbling chaotically, the local heating could have shifted unpredictably, triggering jets in sudden, violent bursts. The data we have hint at such complexity. Observations showed alternating regions of brightness and dimming, patterns consistent with rotation but too irregular to fit a simple spin model. It's possible that as one hemisphere fractured, its mass distribution changed, altering the rotation itself, a self-modifying motion that further complicated the dynamics. Each burst of gas might have spun the comet faster, changing its orientation and exposing new surfaces to the sun. In effect, it was chasing its own tail, spiraling toward collapse. This idea of runaway loss also fits with another curious aspect: the timing. The strongest activity of 3I Atlas occurred not long after perihelion, rather than before it. For ordinary comets, maximum outgassing usually coincides with the moment of closest approach, when solar heating is most intense. The delay suggests that internal processes continued long after the external heat began to fade. That lingering activity implies stored energy, perhaps in the form of pressurized gases or latent heat trapped beneath layers of dust. Once released, that energy would drive sublimation from within, even as the comet began to move away from the sun. To visualize this, think of a frozen sponge soaked in volatile material. The outer layers thaw first, forming a crust that traps heat beneath. When that inner pressure finally breaks through, the result is explosive, unpredictable, and unstoppable until equilibrium is reached, or until the object disintegrates entirely. 3I Atlas may have been living through that very process, its exponential curve of mass loss the mathematical signature of a slow internal catastrophe. It's worth noting that such feedback behavior isn't unique to comets. We see it throughout nature, from chemical reactions that feed on their own byproducts to ecological collapses where one change accelerates the next. In each case, there's a threshold where control is lost. The beauty and the terror of exponential growth is that it feels harmless until it's far too late. For 3I Atlas, that threshold may have come at Perihelion, the moment when the sun's energy tipped the balance. Loeb's team used the observed data to estimate how much energy would be required to sustain the observed gas flow. The answer was staggering, more than could be delivered by the sunlight striking a 5.6-kilometer object. Unless the surface area had somehow multiplied, the comet was effectively producing more energy output than it received. In thermodynamics, that's impossible unless the system is drawing from internal reserves, chemical, structural, or otherwise. Perhaps volatile compounds stored under pressure released energy of their own, or maybe the collapse of the nucleus exposed so much fresh ice that sunlight could finally reach its full potential. Either way, the curve was too steep to ignore. There's something strangely human about this pattern. We too have moments when change begins slowly and then races ahead faster than we can comprehend. Knowledge, population, even technology, each follows exponential growth until it meets its limits. In that sense, 3I Atlas is a cosmic mirror, showing us what happens when growth outruns stability. Nature, it seems, follows this rhythm everywhere, from galaxies forming stars to comets losing mass. Still, the scientific implications are profound. If the exponential mass loss observed in 3I Atlas is real, it means our current models of cometary behavior are incomplete. They assume steady-state processes, linear or at most quadratic relationships between heat and activity. But interstellar bodies might operate in a different regime, one dominated by structural feedback and internal chemistry. Understanding that could reshape how we interpret other anomalies, like the mysterious acceleration of 1I Oumuamua. So, what could cause this runaway feedback in physical terms? One possibility is phase transitions, when certain ices, such as carbon monoxide or methane, reach specific temperatures. They can undergo abrupt changes from solid to gas, releasing latent heat that accelerates further sublimation. Another is mechanical fragmentation, the splitting of the surface into multiple smaller pieces, each with its own exposed area. That instantly multiplies the effective surface exposed to sunlight, raising the sublimation rate exponentially. If 3I Atlas fractured into dozens of smaller bodies at perihelion, that would fit the data perfectly. But, as with all things in science, the challenge is proof. Direct images of fragmentation are rare. What we see instead are indirect signs: a spreading coma, uneven brightness, the disappearance of the nucleus. The Hubble Space Telescope captured faint indications that 3I Atlas might have indeed begun to separate, but the evidence was inconclusive. What we can say is that the pattern of light and the behavior of its tail were consistent with a body breaking apart. And here's where the exponential nature becomes even more fascinating. If the comet truly fragmented, each new piece would itself begin to sublimate, creating its own jets and releasing more material. That's an exponential process in space, each fragment feeding the next, just as a single spark can ignite a forest. The system becomes a chain reaction of evaporation and expansion. From a single object, you suddenly have a swarm, each contributing to the collective glow we see from Earth. This could explain the immense size of the visible tail and the long-lived activity after perihelion. Even as the main body faded, its fragments continued to interact with sunlight, prolonging the show. What began as a single comet might have ended as a cloud of debris spanning millions of kilometers. And yet, from our distant vantage point, it all looked like one continuous phenomenon, a reminder of how scale and perspective can deceive. The exponential mass loss also raises philosophical questions about balance and inevitability. Was the destruction of 3I Atlas an accident, or was it written into its very structure from the beginning? Every comet that approaches a star faces the same choice: to endure or to yield. Perhaps this one, forged in another system, carried within it the memory of a different sun, a chemistry tuned to another kind of light. When it met ours, the resonance was too much. It sang itself apart, and that image of a comet unraveling in harmony with the very light that revealed it is strangely moving. For in its disintegration, it told us a story we could not have learned otherwise, a story of feedback, of fragility, of the thin line between order and collapse. Now, as the data settle and the light fades, scientists are left with models and equations trying to reconstruct that final dance. How many fragments were there? How fast did the rate double? What parameters governed the feedback? Every answer seems to open a new question, and every question points toward one crucial next step. If exponential loss did occur, then fragmentation must have followed. And to understand fragmentation, we must study what happens when a comet truly breaks apart under the sun's relentless gaze. And that, I suppose, brings us to the next chapter in this unfolding story, the moment when 3I Atlas may have crossed from being one body into many, scattering itself into fragments that now drift silently through the solar wind, like echoes of a single cosmic heartbeat. When an object breaks apart in space, the moment is almost invisible. There is no sound, no violent flash, no shock wave rippling through a medium to tell the universe that something has ended. Instead, the disintegration happens in silence, an unraveling of gravity's hold, a quiet surrender to sunlight and internal strain. For 3I Atlas, that silence may have been the final act of its extraordinary encounter with our sun. After the exponential surge of mass loss, after the jets tore open its fragile structure, the next logical step was fragmentation. It is the natural consequence of imbalance. When an object can no longer dissipate energy evenly, it divides, as if breaking apart is the only way to survive, even for a moment longer. Avi Loeb's calculations had hinted that if the comet truly lost as much material as the numbers suggested, its surface area must have increased dramatically, by a factor of perhaps 16. To achieve that without violating the conservation of energy, the nucleus would have had to split into multiple pieces. If each fragment exposed new ice to sunlight, the total sublimating area could expand rapidly enough to match the observed gas flow. In simple terms, one body would become many, each smaller piece carrying forward the legacy of the original. But this process, while mathematically elegant, is physically violent. The structural stresses required to cause such a breakup are immense, born from both thermal expansion and rotational strain. Picture it. As 3I Atlas neared the sun, its surface heated unevenly. The day side expanded while the night side remained cold. Tiny fractures opened, then deepened, extending kilometers below the surface. At the same time, jets of escaping gas exerted torque, slowly altering the rotation rate. A slight spin-up, perhaps only a few percent faster, could send centrifugal forces surging through the porous interior. The object, already weakened by its own sublimation, began to pull itself apart. Once the first fracture formed, the stress redistributed to surrounding regions, creating a cascading failure. Within hours, the solid nucleus could have transformed into a loose assembly of fragments, bound only by mutual gravity and the faint cohesion of dust. This is not speculation without precedent. The solar system has witnessed such events before. The most famous example is Shoemaker-Levy 9, the comet that broke into a train of 21 fragments in the early 1990s after passing too close to Jupiter. Its fate was sealed by tidal forces, gravity stretching it beyond endurance. Each fragment became a separate nucleus, orbiting in a slow parade until, months later, they plunged into Jupiter's atmosphere, one by one, leaving scars the size of Earth on the planet's clouds. That was the first time humanity had observed a comet in the act of self-destruction. It taught us that comets are not solid rocks, but delicate agglomerates, fragile as ancient snow. 3I Atlas, of course, faced no tidal disruption from a giant planet. Its destroyer was light itself. The same sunlight that fuels life on Earth acted here as a scalpel, slicing away at an interstellar body unaccustomed to such intensity. If it did indeed fragment into 16 or more pieces, the geometry of those fragments could explain the persistent brightness long after the supposed disintegration. Each new surface would sublimate vigorously, releasing more dust and gas, creating a glowing halo that merged into one blurred image when seen from afar. From our vantage point, it would appear as if the comet were still intact, even as it slowly dissolved into a swarm of icy shards. It's humbling, isn't it? To realize that what we observe in the sky may not be a single body at all, but the collective shimmer of many smaller ones moving together through space. Every fragment reflects sunlight. Every piece contributes to the whole, like the scattered notes of a fading song. And yet, within that apparent unity lies the truth of disintegration. 3I. Atlas had become a cloud, a family of fragments bound only by the shared trajectory of their origin. The physics of fragmentation is, in some sense, the physics of failure. It begins with stress accumulation, internal pressure from trapped gases, external pressure from sunlight, mechanical strain from rotation. As those stresses exceed the material strength, cracks propagate. But here's the strange thing. The act of breaking releases energy, which in turn accelerates further fragmentation. Each fragment carries its own momentum and internal tension. Smaller pieces may split again, producing even more surface area, until the process reaches a natural limit where the fragments are too small to tear apart further. What remains is dust, each grain a survivor of the original body, still following the same orbit, still whispering of its parent's fate. In 3I Atlas's case, the pattern of observed jets supports this idea. After perihelion, the tail appeared to widen, spreading across millions of kilometers, its curvature shifting slightly, as if influenced by multiple sources rather than one. The brightness distribution became smoother, lacking the sharp condensation expected from a single nucleus. To some astronomers, that was the signature of fragmentation, the telltale diffusion of light that occurs when a comet transitions from structure to chaos. Yet, as with all scientific stories, the evidence is indirect. No telescope captured the moment of rupture itself. We see only the aftermath, the traces of dust, the changing angles of reflected sunlight, the gentle fading that followed. And in that absence of direct observation lies both the frustration and the beauty of astronomy. We infer the violent from the serene, the invisible from the faintest flickers of light. It's like listening to a symphony performed on the other side of the universe and guessing which instruments played which notes. Loeb's interpretation remains cautious but compelling. He does not claim certainty, only consistency. The data align too neatly with the hypothesis of fragmentation to ignore. The exponential rise in mass loss, the subsequent broadening of the coma, the apparent increase in effective surface area, all point toward a body that broke apart rather than merely evaporated. If that is true, then 3I Atlas joins a small but significant group of comets that could not survive their close approach to a star. There's something profoundly symbolic about that. A wanderer from another system travels for perhaps millions of years through the cold, interstellar dark, untouched by any warmth. Then, for the first time since its birth, it passes near a star, and the encounter proves fatal. In that moment of contact, it reveals its secrets, its chemistry, its fragility, its age. Then it dies, leaving only data and dust. And in doing so, it teaches us something we could never have learned otherwise. Perhaps that's why the comparison to Shoemaker-Levy 9 feels so apt. Both events remind us that destruction is also revelation. When a comet breaks apart, its inner layers, usually hidden beneath insulating crusts, are exposed. Spectral analysis can detect compounds that would otherwise remain invisible. The gases released carry the fingerprints of the environment in which the body formed. In that sense, 3I Atlas's breakup, if confirmed, is not a loss, but a gift, a glimpse into the materials of another solar system, delivered by its own demise. You see, fragmentation is a universal language. Stars, planets, even galaxies follow it. Under enough pressure, all structures yield. It is not weakness. It is transition. The same process that shattered 3I Atlas builds rings around planets and dust belts around stars. The same physics that split a comet's nucleus shapes the cosmic dust that eventually forms new worlds. Matter cycles endlessly between coherence and collapse, and each time it leaves behind patterns that echo across scales. For 3I Atlas, those echoes might still be drifting somewhere beyond Mars, a faint band of particles stretching along its orbit. In time, those fragments will disperse entirely, carried away by solar radiation and the wind of charged particles streaming from the sun. They'll become part of the interplanetary dust, mingling with the debris of our own system. Perhaps one day, centuries from now, a meteor shower will flash faintly in our sky, its particles, tracing back to this interstellar visitor that once blazed so briefly in our telescopes. The cosmos has a way of recycling even its most fleeting stories. But before we consign 3I Atlas to dust, there's one more question worth asking. How exactly would such a breakup unfold? Would it happen all at once, a catastrophic shattering, or in slow motion, with fragments peeling away over hours or days? Observations of other comets suggest a combination. The first fracture releases energy, altering the body's spin and trajectory, which triggers more fractures. In some cases, fragments remain close together, connected by faint bridges of gas and dust before drifting apart. In others, the pieces scatter immediately, forming long trains like beads on a cosmic string. The number 16, Loeb's estimate of how much the surface area must have increased, fits remarkably well with such scenarios. If each fragment were roughly a quarter the diameter of the original, the total surface exposed to sunlight would increase by a factor of about 16, matching the observed energy budget. The mathematics at least works beautifully. Whether reality followed that exact pattern, we may never know. But the alignment between theory and observation is difficult to ignore. Still, fragmentation raises new mysteries. How do the fragments interact with one another? Do they collide, exchanging dust and gas? Does the collective outgassing alter their shared trajectory, nudging them subtly off the predicted path? These are not trivial questions. They touch on the broader dynamics of debris fields, on how the remains of one object can evolve into entirely new structures. In that sense, the story of 3i Atlas might not have ended with its disintegration at all. It may have simply changed form, continuing as a swarm rather than a single entity. That idea of persistence through division is oddly comforting. The comet didn't vanish. It diversified. It became a constellation of its own making, each piece carrying the same motion, the same memory of its journey from another star. If one could see it up close, perhaps it would resemble a slow ballet, shards drifting through sunlight, trailing wisps of vapor like translucent ribbons. Even in death it would be beautiful. And so we are left with a paradox. The destruction that ended 3i Atlas also multiplied its presence. By breaking apart, it became more luminous, more visible, more revealing. The increase in surface area that doomed it also ensured that we could study it in greater detail. Its demise was also its discovery. Science, like the cosmos itself, often advances through such contradictions. But fragmentation is not the final question. It is merely the middle act. The pieces that formed from that breakup continued to evolve under the influence of solar radiation and gravity. They drifted apart, and yet, in doing so, they opened a new chapter, one that invites us to predict what might happen next. For if those fragments remain coherent, they will follow their own delicate paths through space, spreading out like threads in a celestial tapestry. And from Earth, in the weeks and months that followed, astronomers kept watching, hoping to catch a glimpse of how that process unfolded. And that, I suppose, leads us naturally to the next question, the story of what came after the breakup. How the fragments of 3i Atlas behaved in the weeks that followed, what the telescopes saw, and how those observations might finally confirm whether this interstellar traveler truly disintegrated, or if, somewhere out there, one piece still endures, gliding silently away into the dark. After the suspected breakup of 3i Atlas, all eyes turned to the sky. The days and weeks following Perihelion were crucial, for in them lay the answer to the great question: had the interstellar visitor truly disintegrated, or had it somehow survived the furnace of the sun? Astronomers knew that if the nucleus had fractured, the fragments would begin to drift apart, slowly at first, and then more clearly under the influence of sunlight and gravity. Each piece would follow a slightly different trajectory, spreading like sparks from a dying ember, their motion shaped by the invisible hand of the solar wind. The process is subtle, but relentless. When a comet breaks apart, its fragments do not immediately scatter wildly into space. They separate along the same orbit, their differences in velocity measured in mere meters per second. Over time, those small variations compound, stretching the debris into a string of pearls that may extend millions of kilometers. The pattern can be predicted if we understand the forces at play: solar radiation pressure, outgassing jets, and the gentle but persistent tug of tidal effects. For 3i Atlas, these predictions became a kind of scientific prophecy, a roadmap of what telescopes should see in the following weeks if fragmentation had indeed occurred. The first expectation was brightness variation. A cloud of fragments tends to spread the reflected light over a larger area, producing a diffuse glow rather than a concentrated point. Observers reported exactly that: a gradual softening of the nucleus, its once distinct shape blurring into a misty haze. The second expectation was the emergence of secondary condensations, tiny knots of brightness within the coma, marking the positions of individual fragments. Some images hinted at these, faint and uncertain, like ghostly echoes of the original body. Were they real, or were they artifacts of distance and instrumentation? The debate, as always in science, was patient and cautious. The next few weeks became a global watch. Amateur astronomers with backyard telescopes joined professionals using observatories across both hemispheres, all peering into the fading arc of the comet's path. The data streamed in: changes in light curves, spectral shifts, variations in tail structure. Each piece of information was a clue, a whisper from the fragments themselves. The tail, once thin and directed, began to fan out, suggesting that multiple sources were contributing to the gas and dust. A single nucleus could not produce such a wide spread. Only a swarm could. Loeb's hypothesis found its strongest support in those subtle evolutions. If 3I Atlas had split into 16 or more pieces, their combined outgassing could explain the lingering brightness, the asymmetric jets, and the slow fading that followed. The fragments, each smaller than the original, would sublimate rapidly, their lifespans measured in weeks rather than months. Yet collectively, they would sustain the illusion of a single glowing object long after the nucleus itself was gone. It was, in essence, the comet's afterimage, an echo of its former self. You can imagine it, perhaps, a cloud of icy shards drifting silently, sunlight glinting off each one, their faint vapor trails intertwining like strands of silk. To the human eye, it would appear as a soft smear against the stars, its structure ever-changing, alive in a way that defied stillness. And yet, beneath that beauty, a quiet physics was at work, forces so delicate that even the smallest difference in mass or angle could alter the fate of each fragment. The tidal influence of the sun plays a crucial role here. Though not nearly as dramatic as the tidal pull from a giant planet like Jupiter, the sun's gravity still exerts differential forces across a disintegrating body. The side closer to the sun experiences a slightly stronger pull than the far side, stretching the swarm along its orbit. For fragments already weakened by internal stress, this difference is enough to ensure that they drift apart steadily. Over weeks, that gentle separation becomes visible in the evolving morphology of the comet's tail. What begins as a single filament transforms into a fan of diverging streams, each corresponding to a distinct trajectory of dust and gas. But there's another subtler player in this drama: radiation pressure. Every photon emitted by the sun carries momentum. When it strikes a small particle, it exerts a tiny push. For large bodies, this effect is negligible, but for small fragments, especially those only meters or centimeters across, it can be decisive. Radiation pressure can slowly nudge these pieces out of alignment, sending them into slightly different orbits. Some will spiral outward, drifting away from the sun. Others may curve inward, evaporating entirely. The result is a gradual unfurling of the debris field, like petals opening in slow motion. Astronomers use models to predict these outcomes, tracking how the swarm should evolve over time. By comparing those models with real observations, they can test whether fragmentation truly occurred. In the case of 3I Atlas, the data showed exactly the kind of divergence that theory predicted. The apparent elongation of the nucleus, the fading brightness, the diffuse halo, all matched the behavior of a fragmented object dispersing under solar forces. Still, the mystery deepened. Some observations hinted that the central condensation, the brightest point, did not vanish entirely. It persisted faintly, suggesting that at least one major fragment had survived. If so, that survivor might continue its journey, carrying with it the memory of the original structure. Perhaps it would fade slowly, perhaps it would flare again under some future thermal stress. The universe, after all, rarely ends things cleanly. There is always residue, always continuation. As weeks turned into months, the fragments of 3I Atlas grew fainter. Dust dispersed, gas thinned, and soon the object slipped beyond the reach of even the most powerful telescopes. Yet the data collected during that brief window became invaluable. They offered not just evidence of disintegration, but insight into the mechanics of interstellar bodies under solar influence. By analyzing how fast the fragments separated, scientists could estimate their initial velocities, and from that, infer the internal cohesion of the original comet. The numbers suggested something astonishing: 3I. Atlas may have been held together by forces weaker than those in any known solar system comet. It was a cosmic powder, light, porous, ancient. The implications are profound. If interstellar objects like this are so fragile, then their survival through interstellar space is even more remarkable. It means they travel slowly enough and long enough for cosmic radiation to sculpt them into delicacy, yet still reach other systems intact. It also means that when such objects encounter a star, their destruction may be inevitable. The sun, in this sense, becomes both the detector and the destroyer, revealing by unmaking. There's a kind of poetry in that. The light that disassembles these travelers also makes them visible to us. Their deaths become their introduction. Without fragmentation, we might never know their nature, never measure their chemistry, never glimpse their origins. In breaking apart, they communicate. It's as though the universe itself speaks through the act of dissolution. For the observers tracking 3I Atlas, there was also a quiet suspense. The fragments were expected to drift apart visibly over weeks, but the real question was whether any of them would remain dense enough to be detected in later passes. If one survived, its orbit could provide a precious chance for follow-up observation, perhaps even in 2025, when the geometry between Earth, Sun, and the object would allow optimal viewing. That date, whispered through research papers and observatory schedules, became a kind of beacon, a moment to test whether the story was truly over or only paused. In the meantime, theoretical work continued. Models simulated how tidal forces and radiation pressure would shape a debris field of 16 or more fragments. The simulations showed that within a few weeks, the swarm would stretch into a narrow arc spanning tens of thousands of kilometers, its density highest near the leading fragment. That leading piece would carry most of the mass, acting as the gravitational anchor for the rest. But over time, even that would erode, its jets weakening as its ice is depleted. Eventually, the entire system would dissolve into dust, indistinguishable from the background of interplanetary particles. And yet, perhaps not entirely. Some fraction of that dust, caught in the gravitational eddies of the solar system, might linger for years, forming a faint, unseen ribbon along the orbit. Instruments sensitive enough could one day detect it as an excess of micrometeoroids or as a subtle glow of scattered light. If that happens, it would be a final confirmation that 3I Atlas had indeed become part of our solar system's fabric, its interstellar essence now mingled with our own cosmic dust. For now, though, the story rests on observation and inference. The predicted separation, the gradual fading, the diffusion of brightness, all have unfolded as theory suggested. The tidal forces have done their quiet work, drawing the fragments apart until they are no longer distinguishable. But in that dispersal lies a deeper meaning. Every fragment carries not just the material of another world, but also the trace of its journey, the record of how sunlight, gravity, and time sculpted it. In tracking their paths, we are reading the diary of an interstellar traveler written across the void. Perhaps one day, another such object will arrive, and we'll watch it more closely, with better instruments and a clearer sense of what to look for. We'll be ready to catch the moment before fragmentation, to see the physics unfold not in hindsight, but in real time. For now, we have 3I Atlas as our teacher, a comet that came from nowhere, blazed briefly in our sky, and then dissolved into lessons. And as the last of its fragments faded from sight, astronomers began to wonder, what if the breakup had never occurred at all? What if the models were wrong, and 3I Atlas, though changed, somehow remained whole? That possibility, faint but intriguing, leads us to the next question. If the comet did not break apart, then what else could explain its strange behavior under the sun? What other forces might have been at work, invisible yet decisive, guiding its motion in ways we still struggle to understand? But what if, after all the light curves, all the models, and all the spectral analysis, 3I Atlas had not broken apart at all? What if, instead of dissolving into fragments, it had remained whole? Its strange behavior, not the echo of a catastrophic disintegration, but the signature of some deeper, subtler mechanism we do not yet understand. That thought lingered among astronomers in the months after the comet vanished from view. It was a question that refused to fade, because the truth is, much of the evidence for fragmentation is indirect. The light we see is an interpretation, not an image. The tails, the brightness changes, the patterns in the dust, all of them can be explained by other means if one dares to look beyond the familiar script. Suppose for a moment that the nucleus endured. Then everything we thought we knew about its exponential mass loss and apparent expansion must be reconsidered. Could there be another reason for those immense jets? Could there be a process hidden within the physics of light and matter, capable of mimicking the signs of breakup without any physical fragmentation at all? That was the line of thought pursued by a small but persistent group of researchers who began to model 3I Atlas as a single coherent body responding to unusual internal dynamics. You see, the difficulty lies in how much we assume. When a comet brightens beyond prediction, the simplest explanation is that it has increased its surface area, either by shedding dust or splitting apart. But brightness does not always equal size. In some cases, changes in reflectivity or particle composition can produce the same effect. A shift in the ratio of ice to dust, or in the density of the surrounding gas cloud, could alter how light scatters through the coma. Even a minor change in the shape of the jets could make the object appear larger or more diffuse than it really is. Perhaps 3I Atlas was not disintegrating, but merely venting its gases in a chaotic pattern, spreading its dust unevenly until it mimicked the signature of fragmentation. If that were true, then the apparent increase in surface area would be optical illusion, a byproduct of geometry and perspective rather than of destruction. The comet could have rotated in such a way that its brightest face was presented toward Earth for several days, followed by a reorientation that made it seem to fade. The tail, shaped by solar wind and magnetic fields, might have widened due to variable outgassing, rather than to the dispersal of multiple fragments. The sun's influence, always complex, could have exaggerated these effects in ways our models do not yet capture. There's also the possibility that 3I Atlas had a highly irregular surface composition. If certain patches were rich in more volatile ices, carbon monoxide or ammonia for instance, then localized jets could erupt suddenly as those ices sublimated, giving the appearance of an exponential surge. Once those pockets were exhausted, the activity would subside, producing the illusion of a collapse. In reality, the nucleus would remain intact but scarred, its surface pitted with the remnants of those eruptions. The cycle of flare and fade could repeat, creating the illusion of gradual fragmentation, even as the core held together. It is not hard to imagine such a world. Picture a rough, porous body tumbling through space, half coated in organic dust, half in ice. As it rotates, sunlight sweeps across its surface like a slow flame, igniting regions in sequence. Jets burst forth, twisting in spirals, each eruption adding momentum that alters the comet's spin. Over time, This chaotic interplay of heating and venting could destabilize its motion without necessarily breaking it apart. The visible chaos would hide an underlying unity, a comet still whole, though battered and transformed. If this scenario is correct, then the question becomes, why does 3I Atlas not fit our models? Perhaps our models themselves are too narrow. Most cometary simulations are built from the behavior of solar system comets, objects that share a common ancestry, composition, and evolutionary history. Interstellar visitors are different. They were born under other suns, in disks of dust with different chemical balances. Their ratios of carbon to oxygen, their crystalline structures, even the way their ices trap gases, all of these could differ profoundly from what we expect. A process that appears abnormal by solar system standards might be perfectly natural for an object from elsewhere. That thought opens a deeper possibility. What if 3I Atlas represents not an anomaly, but a new category of object altogether? A kind of hybrid between comet and asteroid, dense enough to hold its shape, yet volatile enough to display comet-like activity. In that case, its apparent behavior near perihelion would make sense. A tougher nucleus could survive higher levels of stress, releasing gas from fractures without disintegrating. Its surface might act as a patchwork of vents, opening and closing unpredictably as thermal stresses shift. Such a body could easily mimic the observational signature of fragmentation while remaining physically intact. Some astronomers have even proposed that 3I Atlas could be covered by a crust of refractory material, minerals that resist heat, beneath which lay reservoirs of supervolatile ices. The crust could act as a pressure valve, trapping gas until the internal buildup became strong enough to break through in sudden bursts. Those bursts, seen from Earth, would look like the flare-ups of a disintegrating comet, yet they would leave the main body unharmed. Over time, the crust would reseal with dust, only to rupture again when the next patch of sunlight reached it. The comet would appear alive with unpredictable motion, not because it was dying, but because it was breathing. There's a poetic symmetry to that image, a traveler from another star inhaling and exhaling under the heat of our sun, its activity a kind of heartbeat written in light. It reminds us that not all violent appearances in nature are signs of death. Sometimes they are signs of adaptation, of resilience. If 3I Atlas endured, it may have shown us that interstellar comets are stronger, more complex than we imagined. Of course, to support such an idea, one must find evidence. Astronomers searched for consistent orbital motion in the aftermath of perihelion, any sign that a coherent body remained. If the comet had truly broken apart, its trajectory should have shifted slightly, each fragment pulled by its own outgassing. If it remained whole, the path would stay stable. The results, while inconclusive, lean toward continuity. The orbital elements did not diverge as drastically as a full fragmentation event would predict. That faint stability, that persistence of motion, became the strongest argument for the survivor hypothesis. And yet, this line of reasoning creates new mysteries. If the comet survived, where did all the dust and gas come from? How could a nucleus of only 5 or 6 kilometers produce such an enormous outflow without self-destructing? The answer might lie in physics we have not yet fully mapped. Energy transfer within porous materials, for instance, behaves in nonlinear ways. Heat can travel along invisible channels, reaching deep pockets without warming the surrounding material. In that sense, 3I Atlas might have functioned like a labyrinth of tunnels, sunlight triggering sublimation in remote chambers, each vent releasing a focused jet that carried dust far into space. Such efficiency would multiply the apparent energy output without requiring the body to enlarge or fracture. Loeb himself, cautious as always, has said that the data do not conclusively prove fragmentation. His phrase, "not adding up," applies equally well to both possibilities. If the comet broke apart, we must explain why we saw no discrete fragments. If it survived, we must explain how it lost so much mass without shattering. Either way, our understanding is incomplete. That tension between destruction and endurance is what keeps the mystery alive. Perhaps that's the real beauty of Three-Eye Atlas. It sits on the edge of our comprehension. It forces us to question what we think we know about how matter behaves under light. The line between breaking and transforming is thin, and sometimes from millions of kilometers away, indistinguishable. When we observe a distant comet, we are always reading from shadows, translating flickers of light into stories about structure and motion. Maybe in this case, the story we told was too dramatic, too human. Maybe the comet did not die. It simply changed. If Three-Eye Atlas remains intact, it means it is still out there now, traveling away from the sun, growing dimmer with each passing day, its gases frozen again, its surface cooled. It would be a faint, invisible point, moving silently toward the edge of the solar system and beyond, back into the interstellar dark. There's something profoundly moving about that idea. A visitor comes, flares briefly in the light of our star, leaves behind more questions than answers, and then returns to the vast, quiet space between suns. And yet, even if it survived, it may not be done with us. Its trajectory, now known with precision, offers another chance. By 2025, the geometry of Earth and the comet's path will align once more, allowing renewed observation under optimal conditions. If a nucleus still exists, telescopes will detect it then, perhaps as a dim point, perhaps with faint residual activity. That moment could confirm or refute everything we think we know. It could reveal whether we witnessed a disintegration or a transformation. And that possibility brings us naturally to the next step, the problem of probability and coincidence. Because if Three-Eye Atlas did survive, if it truly endured its passage near the sun and emerged as a coherent interstellar body, then we must ask how likely it is for such an object to appear in our skies at all. How often do such travelers visit us? And why in the vast emptiness of space did we encounter one so peculiar, so perfectly poised between survival and collapse? When scientists speak of chance, they do not mean luck in the way we usually think of it. They mean the delicate arithmetic of probability, the hidden rhythm that determines how often rare events unfold in the vastness of the cosmos. And when it comes to interstellar visitors like Three-Eye Atlas, probability becomes a language of wonder. Because the simple fact that it appeared in our skies at all, in this brief window of human observation, is something close to miraculous. You see, the galaxy is a sea of stars, each surrounded by its own retinue of planets, asteroids, and comets. Every so often, gravitational interactions fling some of these bodies into interstellar space, where they wander for millions, perhaps billions of years. Most never cross our path. The distance between stars is so immense, and the volume of space so vast, that the odds of one of these travelers passing close enough to the sun to be noticed are staggeringly low. For much of astronomical history, it was assumed we might never witness such a thing. Yet in just a few short years, we have seen not one, but three: Oumuamua, Borisov, and now Three-Eye Atlas. That frequency defies expectation. Before Oumuamua's discovery in 2017, the estimated rate of interstellar objects entering the inner solar system was roughly one per few 100,000 years. After Borisov in 2019, the models were revised to one per century. Now, with Three-Eye Atlas, that estimate must be lowered yet again, perhaps to one per decade. Something has changed. Or perhaps Something in our understanding was always incomplete. Are these objects truly that common, or are we simply becoming better at noticing them? The improvement of our instruments certainly plays a role. Wide field surveys like Atlas and Pan-STARRS scan the entire sky nightly, detecting faint moving objects that would once have gone unseen. The statistical correction for such improved detection rates explains part of the mystery. But even when adjusted, the odds of 3 large interstellar bodies passing through our neighborhood within a single decade remain surprisingly high. It's as if the galaxy has decided to remind us, all at once, that we are not isolated, that we live in a crossroads of stellar debris. Now consider the size of 3I Atlas. Its nucleus, estimated at around 5 to 6 kilometers, places it among the largest known interstellar comets. The probability of detecting such a large body, rather than the countless smaller fragments that pass invisibly, is even smaller. If the distribution of sizes follows the same pattern as in our solar system, large bodies like this should be exceedingly rare. For one to appear within observational reach in such a short time span challenges our assumptions about how interstellar material is distributed. It suggests either that the galaxy is richer in such bodies than we thought, or that we are observing a transient wave, a cluster of debris born from a common event long ago, perhaps the breakup of a planet or the collapse of a distant star system's outer disk. It is tempting to see patterns where none exist, but in this case, the pattern is difficult to ignore. The inclination of 3I Atlas's orbit, almost coincident with the ecliptic, the plane in which our planets move, is statistically unlikely. Most interstellar visitors, entering from random directions, should follow steep trajectories relative to that plane. Yet here was one that traveled almost along it, as though drawn deliberately into alignment with our solar system's architecture. Was it coincidence, or the result of some galactic geometry we do not yet grasp? Avi Loeb himself remarked on this alignment. The odds of an interstellar object arriving so neatly along the ecliptic are small, perhaps 1 in 10,000, depending on the assumptions. It could be chance, of course. But chance has a curious way of clustering in the universe. The same improbable conditions seem to repeat, as though reality has preferences hidden within its randomness. Loeb's question, then, was not one of belief, but of inquiry. If the odds are so low, is there something guiding these trajectories, some mechanism that increases the likelihood of their appearance where we can see them? You see, when scientists talk about probability, they often discover that improbabilities vanish as understanding deepens. What once seemed miraculous becomes inevitable when viewed from a broader frame. The alignment of 3I Atlas with the ecliptic might simply reflect the structure of the local galactic environment. Perhaps the density of interstellar debris is higher along certain stellar streams, remnants of long-lost star clusters that share the sun's motion through the galaxy. In that case, the arrivals of Oumuamua, Borisov, and Atlas would not be isolated events, but samples from a passing current of interstellar matter, a cosmic tide through which our solar system is now drifting. Still, there's an emotional quality to these statistics. To encounter something so rare, so improbable, reminds us of our fragile place in the universe. The numbers may one day explain it, but for now, it feels personal, almost intimate. A handful of atoms once part of another world have passed within reach of our telescopes. They carried within them the chemistry of another sun, the memory of another time, and by sheer probability, by the mathematics of coincidence, they came close enough for us to notice. It is also worth considering that probability itself is shaped by perspective. From the standpoint of the galaxy, interstellar encounters are commonplace. Tens of thousands of comets like 3I Atlas may cross the orbits of distant stars every year. It is only our brief lifespan and narrow window of observation that make them seem extraordinary. If we could watch for 1 million years, these events would unfold as routinely as sunsets. Our sense of rarity is, in a way, an artifact of time, a reminder that we are transient observers trying to read eternity in moments. Still, the coincidence of timing remains haunting. That 3 such visitors should arrive in an age when humanity has the tools to detect them feels almost scripted, as though the cosmos waited until we were ready to look. In another era, they would have passed unnoticed. In this one, they become catalysts for discovery, forcing us to rewrite our models of how material moves between stars. The improbable becomes a doorway to understanding. Now, when we apply probability to the specific geometry of 3I Atlas's orbit, we find something even more intriguing. Its path through the solar system intersected the region near Earth's orbit at an angle that made it observable for several weeks, long enough for detailed study but not so close as to be dangerous. That narrow window of visibility corresponds to a fraction of a degree in orbital inclination and a handful of days in timing. If either had differed slightly, the comet would have passed unseen, lost in the glare of the sun or hidden in the southern sky. It's as if the universe conspired to show it to us, just once, perfectly framed. Of course, science resists the language of fate. What we call coincidence is, in truth, the sum of many independent variables intersecting in just the right way. Yet, as Loeb often says, science begins where coincidence refuses to stay silent. When the improbable repeats, it demands explanation. The appearance of multiple interstellar visitors in such close succession may signal that our galaxy is more dynamic than we've imagined. Perhaps stellar systems regularly exchange material, scattering debris like seeds carried by solar winds. The galaxy, then, is not a collection of isolated gardens, but a single ecosystem, its worlds interconnected by invisible currents of matter and chance. If this is true, then probability itself becomes a bridge between stars. Every time an interstellar object passes through our solar system, we are witnessing a statistical inevitability born from the vast numbers involved. Billions of stars, each shedding trillions of fragments over billions of years. Inevitably, some of those fragments must cross paths with us. What feels improbable on the scale of human lifetimes becomes certainty on the scale of cosmic time. Still, it is hard not to feel awe when probability and reality intersect so perfectly. 3I Atlas was not just a number on a curve, it was a visible reminder that the improbable happens every day in the universe. It reminds us that rarity is not absence, it is simply patience waiting for the right alignment. And yet, within that alignment lies a question that probability alone cannot answer. Why did 3I Atlas behave so strangely once it arrived? The odds of its appearance are calculable, but the reason for its unique behavior remains elusive. Whether it fractured or endured, whether it was natural or something more complex, its path was shaped by forces we do not yet fully comprehend. The statistical improbability of its discovery is mirrored by the physical improbability of its behavior. Both defy expectation, as though the cosmos were offering a puzzle written in 2 languages, one mathematical, one physical. Perhaps that is the true meaning of 3I Atlas's visit. It forces us to reconcile chance with causality, randomness with pattern. In doing so, it reminds us that probability is not destiny, but invitation. Each unlikely event asks us to look closer, to search for the hidden structure that makes it possible. And in that search, we find meaning. By the time 2025 arrives, the comet, or whatever remains of it, will again occupy a position ideal for observation. If we detect it then, we will be able to test not only the physical hypotheses of its survival, but also the statistical ones of its recurrence. Was this encounter a fluke, or part of a larger wave of interstellar material sweeping through our region? The answer will tell us not just about one comet, but about the architecture of our galaxy itself. And that, I suppose, leads us naturally toward the next question, the one Avi Loeb himself hesitated to ask aloud. If the behavior of 3I Atlas cannot be explained entirely by sunlight and sublimation, if the probabilities of its motion and appearance remain so finely tuned, then what other forces, what other kinds of propulsion or pressure might be shaping its path through space? When Avi Loeb asked what other forces might have shaped the path of 3I Atlas, it was not an act of speculation for its own sake. It was rather the natural continuation of a scientist's discomfort with incomplete explanations. The physics of sunlight, sublimation, and gravitational dynamics could describe much of what was seen, but not all of it. The jets, the acceleration, the brightness variations, the improbable energy budget, they each obeyed the laws of motion, yes, but only if one allowed for an unseen hand pushing gently from behind. And so the question lingered, like a low hum at the edge of understanding. If not sunlight alone, then what? You see, when we calculate the acceleration of a comet, we expect its movement to follow Newton's laws precisely. The sun's gravity should dictate its trajectory, and any small deviations are typically explained by the push of gas escaping from sublimating ice. But in the case of 3I Atlas, that push seemed far stronger than the amount of escaping gas could reasonably produce. Loeb and his colleagues compared the expected sublimation rates to the observed acceleration and found that the two were mismatched by orders of magnitude. Something else was adding momentum. Something was producing motion without mass loss in proportion to its power. That was the beginning of what Loeb called non-gravitational acceleration without a clear physical mechanism. Now, one might argue that this is simply an artifact of poor data. After all, small errors in estimating brightness or size can lead to large discrepancies in calculated force. But this is precisely why the comparison to Oumuamua became so important. That earlier interstellar visitor had displayed a similar anomaly, an acceleration that could not be explained by the faint outgassing of any detectable material. The same mystery repeating itself in two separate objects could no longer be dismissed as coincidence. Nature, it seemed, was whispering the same secret twice. The simplest explanation is that both objects were propelled by sunlight pressure, the same gentle force that moves solar sails. Light carries momentum, and though each photon is tiny, the sum of countless photons over a large area can produce measurable thrust. For an object the size of 3I Atlas, however, the effect should be negligible unless the body were unusually light or unusually reflective. That led Loeb to propose a provocative idea. What if the object's geometry, not its composition, was responsible? If 3I Atlas were thin, perhaps even sheet-like, it could respond to sunlight far more strongly than a dense, solid comet would. It is a delicate line between hypothesis and imagination, but science has always advanced by daring to walk it. Loeb did not claim that 3I Atlas was artificial. He simply asked whether the forces acting on it resembled those that might act on a light sail, a broad, thin structure designed to harness radiation pressure for propulsion. The mathematics worked. A sufficiently large but lightweight object with a high reflectivity and low density could indeed experience the kind of acceleration observed without significant outgassing. But what natural process could create such a structure? Could a fragment of cosmic dust, or a layer peeled from a larger body, behave this way? Perhaps, he mused, 3I Atlas was not a typical comet at all, but a remnant of some ancient collision, an interstellar sheet of carbonaceous material, or a sliver of frozen gas, compressed and hardened by eons in space. The sun's light would push on it unevenly, producing the strange patterns of motion and brightness we observed. In that case, the same physics that drives artificial solar sails would apply to a purely natural object. The boundary between nature and engineering would blur, not because the object was made by intelligence, but because physics itself makes such designs efficient. Still, others were not so sure. They noted that 3I Atlas did produce visible jets, which implied sublimation. A light sail would not. Yet the geometry of those jets, uneven, directional, and disproportionately powerful, still hinted at something more complex than a simple outgassing comet. One could imagine perhaps a hybrid situation, a body with broad, fragile surfaces that caught sunlight like sails while also venting gas through porous channels. That combination could amplify acceleration beyond what sublimation alone could achieve. It would be a natural sail, sculpted not by design, but by erosion, light itself carving the structure that later amplifies its effect. And that, I think, is the poetry hidden in this science. The universe builds its own sails. In the vast emptiness between stars, fragments drift for eons, slowly weathered by starlight and cosmic rays until only their strongest, thinnest layers remain. When such a fragment passes near a star, it behaves not like a rock, but like a sail, sensitive to light, reactive to radiation, alive with motion. 3I. Atlas might have been one such relic, a shard of cosmic fabric fluttering briefly in the solar wind. Yet even that explanation raises new questions. If sunlight alone drove the acceleration, why was the effect so directional? Why did the jets and brightness shifts seem to follow a pattern inconsistent with uniform illumination? Some suggested that magnetic fields might play a role. The solar wind, carrying charged particles, can interact with certain materials, especially those containing metals or ionized dust, to create Lorentz forces that subtly alter trajectories. In that case, the push would come not from light but from plasma, from the electric heartbeat of the sun itself. That idea, while speculative, fits with recent discoveries showing that comet tails often respond to solar storms in dramatic ways, twisting and brightening in synchrony with bursts of charged radiation. If 3I Atlas carried even a small electric charge, its motion through the solar wind could have been influenced in ways we are only beginning to model. Its jets, charged with ions, might have acted like miniature thrusters, steering the body slightly off its gravitational path. To an observer millions of kilometers away, that deviation would appear as unexplained acceleration. What looks like mystery might simply be complexity, a dance between light, plasma, and dust too intricate for our current instruments to disentangle. But Loeb, ever curious, kept returning to the deeper question. If we allow for light pressure as a significant force, we must also confront its implications. Because if radiation pressure can push a natural object to measurable speeds, then it can also serve as a form of propulsion for artificial ones. And that means the boundary between the natural and the technological in our observations grows thinner. When we detect non-gravitational acceleration, we cannot simply assume it is natural. We must consider both possibilities, without prejudice and without fear. That is not sensationalism. It is scientific discipline, applied equally to the ordinary and the extraordinary. You see, the history of astronomy is filled with moments when something inexplicable turned out to be ordinary, and others when something ordinary hid the extraordinary. When pulsars were first discovered, their regular radio signals led scientists to nickname them little green men. Within months, they were understood as neutron stars, spinning relics of supernovae. But that initial openness, to consider all options, was essential to discovery. Loeb's willingness to entertain unconventional explanations continues that tradition, not as belief, but as method. And perhaps there's a deeper philosophical current here. The forces acting on Three-Eye Atlas, light, heat, gravity, plasma, are the same forces that act on everything in the cosmos. Yet, in the right combination, they can produce effects that seem almost deliberate. The universe, through its natural laws, is capable of sculpting behavior that mimics intention. A sail doesn't have to be designed to catch light. It only has to exist in such a way that light finds it. In that sense, Three-Eye Atlas might represent the intersection of physics and the appearance of purpose, a phenomenon where the mind perceives design in what is merely elegant inevitability. Still, the question of propulsion remains central. If sunlight could truly account for the observed acceleration, then Three-Eye Atlas must have possessed an extraordinarily low mass-to-area ratio. Its density would need to be less than that of aerogel, lighter than any solid known to form naturally. Could such material survive the journey through interstellar space? Could it withstand collisions with dust and cosmic radiation for millions of years without disintegrating? Theoretically, perhaps yes, if it were large enough and coated with a protective layer of organic compounds. Nature is resourceful. Given enough time, even fragile materials can endure. If, on the other hand, the acceleration was not due to light pressure, then we are left with an even greater mystery. No known natural process could produce such thrust without significant outgassing, and yet no massive gas plumes were detected. Could there be a hidden source of propulsion, something within the object's structure that responds to energy differently than known materials? Some have speculated about exotic ices or trapped gases that release energy through phase transitions unknown in our solar system. Others have proposed resonance effects between solar radiation and molecular vibrations within the body. These ideas remain untested, but they remind us that the chemistry of other star systems might surprise us. The mystery of Three-Eye Atlas, then, becomes a study in humility. Each new explanation expands the boundaries of what we consider possible. Whether it was sunlight, plasma, or some other subtle mechanism, its motion reveals that interstellar objects operate in regimes of physics we have only begun to explore. The galaxy, it seems, is not a quiet place of static stones, but a living sea of reactive, dynamic matter, each fragment telling a different story of interaction between energy and form. As the comet fades into darkness, its trajectory continues outward, carrying the secret of its propulsion with it. We can follow it with equations, trace its path with telescopes, but the truth of its behavior may remain hidden until another object, another visitor, arrives to show us more. Perhaps one day, we will capture such a traveler before it nears the sun, studying its surface, its response to light, its chemistry. Then, at last, we might learn whether radiation pressure alone can sculpt such grace, or whether some other stranger engine hums beneath the surface. And so, the story of Three-Eye Atlas leads us inevitably toward the next question, the question of comparison. For if light and plasma can drive motion, if interstellar fragments can mimic sails or thrusters, then what do we make of the patterns that link them all? How do we connect the mysteries of Three-Eye Atlas with those of its predecessors, Oumuamua and Borisov? What do their similarities tell us about the architecture of our galaxy, and what do their differences whisper about the diversity of worlds beyond our sun? By the time 2025 draws near, the faint path of Three-Eye Atlas will have carried it far beyond the orbit of Mars, into a region of space where sunlight is weak and the shadows of the outer planets stretch endlessly. And yet, on December 19th of that year, the geometry between the Earth, the Sun, and that elusive interstellar body will align in such a way that, for the first time since its departure, we will be able to look for it again. Astronomers call this the point of optimal observation, A brief window when the glare of the sun diminishes, the angle of reflection sharpens, and the returning light can once more reach our telescopes. It will be the moment of truth, the one chance to determine whether 3I Atlas truly disintegrated at perihelion, or whether, against all expectations, it survived. You see, when an object like 3I Atlas fades from view, it doesn't simply vanish. It recedes into silence, its motion predictable only through equations, its brightness a memory. Every so often, its projected orbit brings it into a position where our instruments can search again, testing theory against reality. December 19th, 2025, marks exactly such a point. By then, enough time will have passed for the debris, if any remains, to disperse. If 3I Atlas did fragment, the cloud should by then have spread over millions of kilometers, forming a faint arc detectable through sensitive imaging. If it survived, a single point of light, dim but steady, will confirm the persistence of its nucleus. Either outcome will reshape the story we've told ourselves about what happened near the sun. The preparation for that observation has already begun. Across observatories from Chile to Hawaii, astronomers have marked the date on their schedules. The James Webb Space Telescope, if available for tracking, could provide infrared data capable of distinguishing between dust and solid body. Ground-based facilities equipped with wide-field detectors, such as the Vera Rubin Observatory, will monitor the region weeks in advance, mapping any faint moving source. Even amateur astronomers armed with new high-sensitivity cameras will join the effort, scanning the sky for a sign, a flicker, a glint, a motion against the stillness. For scientists like Loeb, the anticipation is almost philosophical. The data gathered that night could decide which story of 3I Atlas is true. If no object is found, if the sky remains silent, it will confirm the hypothesis of complete disintegration. The exponential loss of mass, the immense energy outflow, the spreading coma, all would align with a model of catastrophic breakup. But if something is seen, if a nucleus reappears where calculations predict, then everything must be reconsidered. The equations that failed to balance will have to be rewritten, and the mystery of not adding up will deepen. The challenge, of course, lies in the faintness of the signal. By December of 2025, 3I Atlas will be far dimmer than when first discovered. Its brightness will have decreased by several magnitudes, perhaps beyond the reach of most instruments. Yet modern telescopes can detect astonishingly faint light. By comparing the current brightness to predictions, astronomers will estimate whether the object remains intact or exists only as a trail of dust. A solid body reflects light consistently. A cloud diffuses it unevenly, scattering photons in unpredictable patterns. The difference, while subtle, is measurable. If 3I Atlas reappears as a coherent source, scientists will then study its spectral fingerprint. The light reflected from its surface, or from its remnants, will carry information about its composition. The infrared range will reveal whether volatile ices remain, whether the object still bears traces of activity, or whether it has become inert. A surviving nucleus would confirm that the forces acting at perihelion, however extreme, were insufficient to destroy it completely. In that case, we might be witnessing a kind of resilience unknown among comets, perhaps a composition denser, stranger, more alien than anything found within our solar system. And yet, if no trace is found, that too will be revealing. The absence of evidence is not emptiness. It is a measurement in itself. It would mean that the object's material dispersed beyond detectability, that sunlight and sublimation consumed it entirely. The dust that once formed its body would now drift invisibly through the solar wind, its atoms joining the endless haze of interplanetary space. In a poetic sense, the comet would have become part of the sun's own breath, its final gesture, merging with the very light that destroyed it. You know, there's something profoundly human about this waiting. For nearly 2 years, the scientific community will prepare for a single night of observation, a window only hours wide. The precision of it, the choreography of telescopes across the globe, all turning toward the same point in the sky, feels almost ceremonial. It's a ritual of curiosity, a collective act of patience. Science, at its heart, is not about answers. It's about waiting long enough for the universe to speak again. There's also the question of what new technology might bring by then. By late 2025, the next generation of detectors and space-based telescopes could offer levels of sensitivity unimagined a decade earlier. Adaptive optics will sharpen ground-based imaging. Machine learning algorithms will filter noise, teasing faint signals out of the background. Even if 3i Atlas has dimmed to near invisibility, these instruments might still glimpse it, a thin streak of motion against the black. Each photon captured will carry the weight of years of questioning. If the comet is found, one of the first tasks will be to measure its position precisely. From that, scientists can compare its current orbit to earlier predictions. Any deviation will reveal the forces that acted upon it during its last passage near the Sun. Did it accelerate beyond gravitational expectation, as the earlier data suggested? Did it slow down, implying mass loss and drag from sublimation? Or did it move exactly as a solid, stable object would? Each possibility has profound implications. A confirmed non-gravitational acceleration would strengthen the argument for radiation pressure or other unknown forces. A perfectly gravitational path, by contrast, would suggest that the earlier anomalies were observational errors, or that something changed after perihelion. The results will ripple through astronomy. If 3i Atlas indeed survived, it would become the first interstellar object ever observed both before and after perihelion with measurable stability. We would have, at last, a full picture of an interstellar comet's behavior under the heat of a new star. Such data could refine our understanding of the physical limits of matter forged under different suns. On the other hand, if it is gone, then its disappearance will stand as evidence that interstellar comets are fragile travelers, ghosts that cannot survive their first encounter with a living star. But there is another, quieter question beneath all this. Beyond the equations and light curves lies something more existential. What does it mean to watch an object from another star system die or endure under the light of our sun? What does it tell us about our place in a universe where even fragments of other worlds can pass so close? Perhaps 3i Atlas is a messenger not in the mystical sense, but in the scientific one. It reminds us that the boundaries between systems are porous, that material and memory alike flow from one star to another. Each encounter like this blurs the line between ours and theirs. And maybe that's the deeper reason we wait for December 19th. It's not just to confirm a model, or to prove or disprove a hypothesis. It's to stand at the edge of our knowledge and listen for an echo from elsewhere. To see whether a fragment of another sun still shines, however faintly, under ours. When that night comes, the data will arrive in streams, numbers first, then images. For most, they will look ordinary. A field of stars, a faint blur, a trace of movement. But within those pixels lies an answer years in the making. Whether it's the rebirth of a nucleus or the confirmation of its death, that answer will refine not just our models but our imagination. It will teach us, once again, how to see. And yet, even before the results are known, some astronomers are already looking ahead. They ask, what happens after we confirm what 3i Atlas truly is? If it survived, could future missions chase it, intercept it, study it up close? If it did not, Could we track the dust trail it left behind, sampling its remnants as they drift past Earth's orbit? These questions belong to the next chapter of exploration, the part where curiosity turns into pursuit. Because one way or another, 3i Atlas has changed how we look at the sky. It has shown us that the improbable is not impossible, that even in the emptiness between stars, stories are moving toward us. And when December 19th, 2025 finally comes, the telescopes will be waiting, patient and ready, eyes of glass turned upward. Somewhere out there, in the cold beyond Mars, something will either glimmer or not, and in that quiet difference, we will find our answer. And perhaps, just beyond that answer, another question is already forming. If 3i Atlas truly came from another star, what does its journey tell us about where it began, and what other worlds, still unseen, might yet send their messengers across the dark?